Hello students, this is Dr. Syed Tajudeen, Assistant Professor, Department of Chemistry, C. Abdul Hakim College. In this lecture, we will discuss another very important topic in organic chemistry, that is stereochemistry of organic molecules. It is a topic that is concerned with how the atoms of a molecule are arranged in three dimensions. Stereochemistry is also known as three-dimensional chemistry because the prefix stereo means three-dimensionality. That is three-dimensional arrangement of atoms and molecules and the effect of this on chemical reaction. Okay. Why stereochemistry? What are the importance of stereochemistry? So this is an important topic in pharmaceutical chemistry because the shape of a drug molecule affects both its desired biological activity and its potential. For example, as ibuprofen is used as a drug for primarily for fever because S isomer is biologically active whereas R isomer is biologically inactive. Similarly, or L-DOPA is used for Parkinson's disease as a drug, which is also an biologically active, whereas S isomer is inactive. So before we going in detail about stereochemistry and its applications, so let us have a very basic idea about isomers and isomerism. Isomers are non-identical molecules that have the same molecular formula, that is the same elemental composition. Such pairs of compounds differ in their physical and chemical properties and are called isomers. And isomers are broadly classified into two types. One is constitutional or structural isomers, and another one is stereoisomers. Constitutional isomers are having same molecular formula but different in constitution, that is order of connectivity of atoms. Whereas stereoisomers are also have the same molecular formula and constitution but different arrangement of atoms. Structural isomers or constitutional isomers are further classified broadly into three types. One is chain isomers, differ in the connectivity, that is carbon skeleton, and differ in their physical as well as chemical properties. For example, N-butane and 2-methyl propane. Second one, position isomers. These have same carbon skeleton but differ in position of attached atoms or functional groups along the carbon skeleton. For example, 1-propanol and 2-propanol. And third one, functional isomers differ in the functional group. For example, ethanol and dimethyl ether, alcohol and ether. Ethanoic acid and methyl methanoate, carboxylic acid and ester. Propanone and propanal, ketone and aldehyde. Stereoisomers, which have the same molecular formula but differ in the manner their atoms or groups are arranged. And further, stereoisomers are conformational isomers and configurational isomers. Conformational isomers are stereoisomers which can be interconverted rapidly at room temperature without breaking a covalent bond. Because such isomers can be readily interconverted, they cannot be separated at normal conditions. Whereas configurational isomers, which cannot be interconverted unless a covalent bond is broken. The configurational isomers, again of two types, optical isomers are enantiomers and geometrical isomers. Optical isomers some organic molecules has the ability to rotate the plane polarized light. These compounds were termed optically active compound. When the compound rotates the plane polarized light to an equal degree but in opposite direction, the property of rotating plane polarized light is known as optical activity. For example, molecular formula C3H6O3 represents two enantiomeric lactic acids as shown in this figure. Minus lactic acid rotate the plane polarized light towards left hand side, that is anti-clockwise direction. Plus lactic acid rotate the plane polarized light towards right, that is clockwise direction. Geometrical isomers are the stereoisomers which differ in their spatial geometry due to restricted rotation across a double bond. And these are also called as cis-trans isomers. For example, molecular formula C2H2Cl2 corresponds to two geometric isomers, one is cis-1,2-dichloroethane and trans-1,2-dichloroethane. Optical activity is the ability to rotate the plane polarized light. The instrument used to determine the optical activity is polarimeter. When the compound rotates the plane polarized light to right, that is clockwise, is termed as plus or dextrorotatory small d. But the compound rotates the plane polarized light to left, that is anti-clockwise direction, and it is termed as minus or levorotatory, that is small l. The organic molecule that not able to rotate the plane polarized light is called as optically inactive compound. This picture shows there is experiment for optical activity. Okay, in this picture we can see the difference between a normal light and plane polarized light. The plane polarized light is passing through a chiral compound, means there is no change in the direction. Whereas the plane polarized light is passing through a chiral compound, the direction is either clockwise or anti-clockwise. So dextro plus small d, and do not confuse with this capital D. And levo minus or small l, similarly do not confuse with the capital L. The angle of rotation of plane polarized light by an optically active substance is proportional to the number of atoms in the path of light. Specific rotation. The number of degrees that the plane of polarized light is rotated as the light passes through a solution of enantiomers depends on the number of chiral molecules in sample. This of course depends also on the length of the tube and concentration of the enantiomers. What are enantiomers? Enantiomers are stereoisomers that are non-superimposable on its mirror image. Enantiomers rotate the plane polarized light by exactly the same number of degrees but in opposite direction. So specific rotation can be calculated by using the formula alpha divided by L into C, where alpha is observed rotation, L path length in decimeter, C is the concentration in gram per ml. Hence, specific rotation is defined as the rotation produced by a solution of unit concentration in 1 gram per ml and unit length in 10 centimeter. And condition for optical activity is compound contain chiral center or chiral axis and do not contain element of symmetry. So what is chiral center? Is also called a stereo center, a stereogenic center, which is nothing but an atom connected to four different groups. Suppose the atom is C, that is carbon. It is called as chiral carbon, that is tetrahedron sp3 carbon connected to four different groups. Chirality, that is optical activity. And French chemist Louis Pasteur in 1848 discovered that crystalline optically inactive sodium ammonium tartrate was a mixture of two types of crystal which were mirror images of each other. Each type of crystals, when dissolved in water, was optically active. The specific rotations of the two solutions were exactly equal but of opposite sign. Louis Pasteur discovered sodium ammonium tartrate as crystals of plus and minus. Chiral carbon, a molecule containing a carbon with four different groups, result in a chiral molecule, and the carbon is referred to as a chiral or asymmetric, a stereogenic center. Example of chiral carbon is given in this picture. Okay. So properties of a chiral carbon. Chiral compound is a compound that is optically active and can rotate plane polarized light. Although everything has a mirror image and mirror images are non-superimposable. Actually, chiral molecule contains four different atoms by sp3 hybridization. Chiral compounds are non-superimposable mirror image like our two hands. This picture shows the non-superimposable mirror images. Achiral carbon, a molecule or object that is superimposable on its mirror image, is said to be achiral. In achiral molecule, carbon atom contain at least two same molecule on their hand. So this picture shows some of the achiral mirror images. Chair, an alphabet A, butterfly, which are all gives a superimposable mirror images. See the water molecule, has a achiral molecule. So bromochloromethane is also an achiral molecule. So in general, a molecule with no stereogenic centers will not be chiral. With one stereogenic center, a molecule will always be chiral. With two or more stereogenic centers, a molecule may or may not be chiral. Achiral molecules usually contain a plane of symmetry, but chiral molecules do not. And what is plane of symmetry? Is otherwise called as internal mirror plane. Is a mirror plane that cuts the molecule into two halves so that one half of the molecule is a reflection of the other half. For example, 2-chloropropane has a plane of symmetry and is said to be a chiral, and 2-chlorobutane does not possess a plane of symmetry and said to be a chiral. The compound have plane of symmetry is optically inactive and called mesocompound. An object which cannot be superimposed on its mirror image is said to be chiral, and the property of non-superimposability is called chirality. Thus, our hands are chiral. Similarly, alphabets R, F, J are chiral and A, M, O are achiral. Molecular chirality and asymmetric carbon. Chirality in molecules is usually due to the presence of an sp3 carbon atom with four different atoms attached to it. Such a carbon atom is called a chiral carbon or a chirality center. The presence of a chirality center usually leads to molecular chirality. Such a molecule has no plane of symmetry and exists as a pair of enantiomers. Such a carbon atom is sometimes also referred to as asymmetric carbon atom. So thank you, students. Thank you very much.